If you have two related values dependent on each other, like the number of movie tickets purchased and its total cost, by representing both as variables, you could create an equation representing their relationship. By making the driving variable x and the driven variable y, you can map up all possible value combinations that satisfy this equation on a Cartesian plane. When viewing this graph, we can see the idea of rate of change. For every extra ticket bought, the total cost increases by $5. The formal value used to represent this idea is slope and is calculated by dividing the change in y over a given period by the change in x in the same period. While this value is constant for linear relationships like this, for more complicated ones, the slope changes throughout. Using the method of calculating slope just described on these will only get you the average rate of change. But there are ways, typically outlined in differential calculus courses, to calculate the slope at an individual point, which is called the instantaneous rate of change. If you create a function that gives you the IROC for every x value of another function, you have found the derivative of that function. This is the derivative of y with respect to x. But this only works for an equation with two variables. You have more used the partial derivative. All variables but one are held constant, and the derivative is found with respect to the non-constant. This is called the partial derivative of z with respect to x. Quick interject. A scalar is a value that is just a quantity, like cost. A vector is a value with direction and magnitude, like velocity. For vectors on a Cartesian plane, vectors of size 1 are called unit vectors. These vectors are scaled and summed to represent all other vectors. The simplest notation is this, which omits these unit vectors and just displays the scaling quantities for clarity. If you make an equation that takes in a planar coordinate and returns a vector, you have created what is called a vector field. Okay, back to partial derivatives. If you have a multivariable equation and take the partial derivative of all its variables, these can all be assigned as inputs to a vector field. This field is what's called a gradient and is the multivariable function equivalent to slope. The gradient always returns a vector pointing towards the direction of most increase from that point, which is intuitively like standing in a hilly field and having an arrow always pointing towards the steepest next step you can take. That is the partial derivative in gradient, and this is my submission to this challenge.